Let's talk about logic. Maybe you think it's only logic bots who care about this, but you might be surprised in one form or another. Logic has been around for thousands of years, and it's extra interesting to linguists as a tool for studying language. But just what is logic anyway? I am Rigel Syefa Zarnuji Diza, and this is the link space. So, logic and language might not jump out at you as being related, but actually, the two are super connected. When we try to understand people's sentences, we crunch together their words and other bits into a form that we can take our meanings from. And if you want to do semantics, where people study exactly what language means, there's a whole lot of logic in there. At the least, most of us want to be thinking rationally, or at least sound like we're making sense when we talk. The conclusions we reach and the things we believe should probably have a solid foundation, or we might end up sounds like charms. Great Eastern and Western thinkers alike have spent thousands of years worrying about how to think and argue clearly, but it wasn't until the Greek philosopher Aristotle that we took the first real steps towards understanding why some reasoning works better than others. It turns out that the base of the system for how we understand sentences before considering real-world knowledge or pragmatic concerns can be boiled down to a system of logic. Let's try this. If I tell you that all carnivores eat meat and that some dinosaurs are carnivores, then that must mean that some dinosaurs eat meat too. These three sentences taken together wake up what's called a logical argument. Each of the first two is called a premise, and they both support the third, which is the argument's conclusion. And while this particular argument isn't exactly groundbreaking, there's still something interesting there. Any argument with that shape is a good one. You could plug in whatever you want, and your conclusion will always follow from your premises. You could even use nonsense words, and the argument still works. If you know that all blips are bloops, and that some blobs are blips, then you can be pretty sure that some blobs are bloops. So Aristotle discovered that some kinds of arguments were automatically valid, meaning that if you had true premises, you always get a good conclusion, but his idea of logic was very limited. It only applied to very short arguments, and it only works for groups of things, like old raccoons or some cephalopods. Aristotle's logic could handle sentences about individuals, like Utahraptor or Dromaeosaurus, and it wasn't accommodating enough for complex sentences built out of simpler ones, like T-Rex stomped on the house and he stomped on the car. And you may have noticed, in most conversations, people like building big multi-part sentences and they love talking about specific people. So for dealing with real-life conversations with our pals, we're going to need something a little more well-rounded. That's why, in the following centuries, philosophers developed exactly the kind of system we're looking for. Sentential logic. Sentential logic gets its name from the fact and it takes the simple sentences as its fundamental building block. It's not restricted to talking about groups, and it can take smaller atoms-like sentences and combine them into large molecular ones, using sticky words like and or. Sentential logic has its own little language, but it's not a natural language, like what linguists study. Instead, you can think of it like an artificial language where we have complete control over its inner workings. And that means we have a very good understanding of how it works. Let's zoom in on this setup. First off, sentential logic is completely symbolic, which means it doesn't have any of the messiness of English or any other natural language. It just uses a few basic symbols along with some rules that tell us how to combine simple sentences into more complex ones. So to start, sentential logic uses the letters of the alphabet to represent sentences. For example, we could say H stands for the T-Rex stomped on the house, while C stands for T-Rex stomped on the car. These letters are just handy space having tools They aren't tied to any particular proposition, and so we can link them up to pretty much whatever sentence we want. Once we have our sentences all good and symbolized, the structure building rules of sentential logic use another group of 5 symbols to join them together. These are the logical connectives, and if we want to be technical, they are called the conditional, the biconditional, conjunction, disconjunctions, and negations. And you can see that each of these logical connectives roughly corresponds to some bit of English, but they actually have strict logical meanings. So now, we have a way of building complex ideas in sentential logic. Our earlier examples of T-Rex stomped on the house and he stomped on the car would look like this, with that upside down V to mean and. On the other hand, either Uttaraptor confronts T-Rex or hidden would look something like this. This uses the regular V to mean or and that little flipped L to mean not, because in the second sentence, Uttaraptor did not confront T-Rex. All of these expressions and an infinite number of longer ones are part of sentential logic. They allowed by its syntactic rules, and all of these sentences, simple or complex, have a semantic meaning too. So for simple atomic sentences, it's easy. They either true or false. Depending on the circumstance, it could be true that T-Rex stomped on the house, but false that he stomped on the car. But for bigger sentences, we need semantic rules that tell us how to combine the values of smaller sentences, and that depends on what connectives we choose. To do this, we treat the logical connectives a bit like little truth monsters, feasting on truth and falsehood, and then expelling out the digested remains, and we represent what their diets look like, using truth tables with the food that they eat on the left side and expelled parts on the right. Here's the one for N. So, for our earlier sentences, T-Rex stomped on the house and he stomped on the car. We can look at the right row on the truth table to find out the result. Since we decided that H was true but C was false, we can look on the truth table and see that the whole sentence was false. If we had T-Rex stomped on the house or he stomped on the car, we could look at the truth table for or and figure out that the sentence is true. These truth tables show up a lot in semantics work because they can show us at first glance exactly when a sentence is true. And now that we have a grasp on sentential logic, we not only understand why Aristotle's arguments work, but also a whole slew of other ones, like take an argument that goes something like this: if Dromedaemimas talks to T-Rex, then the T-Rex will stomp on someone. Dromedaemimas did talk to T-Rex, so he will definitely stomp on someone. Written out in sentential logic, it will look like this. So let's examine the truth table for the conditional connective. Symbolized by this little arrow, we see that the only row where the first input and the results are true is the first one, and there we can see that the second input must also be true. The argument works because of the way sentential logic is set up. So, by creating symbols for our sentences and the connectives that join them together, we've increased the precision and clarity of our thought. But so what? It's fair to wonder why any of this matters much at all. But logic has a very special use in linguistics that goes above and beyond its use in other science. That's because logic is able to model language like the mathematical models that physicists use to study the universe. It's something that we understand well, so it's easy to work with. Plus, it's close enough to natural language to be helpful, and it lets us ask some interesting questions that otherwise we wouldn't be able to, like we know that the logical connective and can swap the order of the things without changing the meaning. So like A and B means the same thing as B and A, but we can wonder whether and in English works the same way. And if you think about it, at first the answer seems to be no. Like I can say T-Rex has friends and all of his friends are dinosaurs, but it's weird and redundant to say all of T-Rex friends are dinosaurs and he has friends and T-Rex stomped on the woman and she died means something very different from the woman died and T-Rex stomped on her. So maybe English and it isn't like the logical and after all. Or maybe it is if we take into account pragmatic knowledge like Greece's cooperative principle. We know that we usually want to talk in orderly way. One thing become after another because of the maxims of matter. And we know that we give out just the right amount of information because of the maxim of quantity. So maybe the fact that English's versions of "and" doesn't seem entirely logical is because Greece's maxims are imposed on top of the logic of English. If Greece's maxims can explain why redundant sentences seem weird, or why things have to go in particular order to make sense, maybe language is more like logic than it first seems. Through this, many questions about natural language connectives and topics like it are still open ones. And we'll be exploring more about that when we come back to talk about language and logic in the future. But even with just these basics, logic has already proven itself to be awesomely handy. Way to go, Logic Bot! So we've reached the end of the link space for this week. If you follow this episode to its logical conclusion, you learn that logic was first developed as a way of understanding how sentences relate to each other, and why some arguments are better than others, that philosophers systemized by logic into sentential logic by symbolizing sentences and their logical connections. And that what we learn about the properties of logic can help us to investigate the properties of natural language.